This video is going to go over section 8.1, which is our introduction to circles. We're going to start off with some vocabulary, some of which might be familiar, some of which might be new, but we're going to make sure that we are on a level ground with that. So a circle has a technical definition. It's the set of all points that are equidistant from a given point. So we start with a point that we call our center, and then the circle is any point that is an equal distance from that center. So if I go out to any point on the edge of my circle, it will be the same distance from that center. That distance is called the radius, and the radius is also a line segment whose endpoints are the center and a point on the circle. The plural of radius is radii, so this is my radius. Let's erase those. So the next word is a chord. A chord is a line segment whose endpoints are both on the circle's edge. This is an example of a chord right here. I always like to think about a chord like on a guitar that would pass over the open circle in the middle, right? A chord would connect the two edges of your circle. Now this is another example of a chord. This is a special one though, because it happens to go through the center. So this is a diameter. That's a chord that passes through the center of the circle. Now, a word that might be new to us is a secant line. So a secant line, I like to think about the word slice when I think of secant. So secant, think slice. And it goes through the circle and it slices it, going through both sides just like that. So a secant is a line that intersects a circle at 2 points. A tangent of a circle is going to hit the circle just one time. So a tangent is a line that goes right adjacent to the circle, and it's going to hit it at just one point. And that point has a special name. It's called the point of tangency. Now our last two words are words that we should be familiar with from previous courses. The circumference of a circle is another name for the perimeter. So that's the entire distance around the circle. And the formula for that is circumference is 2 pi times the radius. Or sometimes we say that as the circumference is pi times diameter, since the radius of twice the radius of a circle is the diameter. And then the last word is area. An area of a circle is the amount of enclosed space. The area formula is area equals pi r squared. And when we talk about the area, we are referring to all the space that's enclosed within that circle. Our next definition is of concentric circles. And think about this, I want you to think of con, meaning like together, and centric, meaning center, right? So these are circles that share a center. They are coplanar and have the same center. So if I put another circle around these, and another circle around these, and they're all sharing the same center right here, those are concentric circles. Our last definition here is going to be of congruent circles. So circles are congruent if and only if they have congruent radii. So if AC and BD are congruent, that means the circles are congruent and vice versa. So the next thing we're going to talk about are similarity transformations with circles. So first I want to look from circle A, which is over here, to circle A prime, which is here. And I want to think about a similarity transformation that would map circle A onto circle A prime. So circle A is a circle with a center at 0, 0 and a radius of 2. Circle A prime has a center at 0, 0 and a radius of 4. So my center has not changed. This has not translated at all. But what has changed is my radius. And it's been multiplied by a scale factor of 2. So when I look here, I'm going to have a dilation around the origin by a scale factor of 2 of circle A. So now I want to do the same thing, but going from A prime to A double prime. So we know that A prime is a circle with the center at 0, 0 and a radius of 4. A double prime has a center at 2, negative 2, but still has a radius of 4. So this time, this has not been dilated at all, right? My scale factor is just 1 here, but it has been translated. It has moved. So what I would say here is that there was a translation to the right 2 and down 2 of circle A prime. So because we have a similarity transformation that would map circle A to circle A double prime, we know that those circles are similar. And this will be true of any set of circles. Anytime I have circles, they have to be similar because we could always come up with a similarity transformation that would transform one into the other. So let's look at this example and think about this the same way. We want to map circle B to circle A prime. So circle B has a center at -5, -4. So B has a center at -5, -4. Circle A has a center over here at +5, +4. So I know that this is going to have to translate, right? It's definitely going to have to translate. But my radius also changes. So here, circle B has a radius of 3. Circle A has a radius of 5. So there's definitely a dilation there as well. So let's write our similarity transformation. So I'm going to start with circle B. And the first thing I'm going to do to that is I am going to translate that to the right 10 and up 8. So that takes care of the moving it to the right and up. The next thing I'm going to do is I'm going to dilate that. And so we know we go from a radius of 3 to a radius of 5. So my scale factor here is 5/3. Now the question is, where is the center of this? So the first thing we did was translate to our new center. And so the center of our dilation is going to be at point A, which is at 5/4. So this would be a similarity transformation that would map circle B to circle A. So some more definitions, angles and arcs in circle. A central angle is an angle whose vertex is at the center. And the measure of the central angle is equal to the measure of its corresponding arc. So if I know that this angle is 30 degrees, that means that this arc that it intercepts or it cuts is also 30 degrees. A minor arc is an arc that is less than 180 degrees. A major arc is an arc that is more than 180 degrees. So if I look at this original picture that I had over here to the right, this blue arc is my minor arc. It is less than 180. But the orange arc that goes from the same two endpoints but goes the other way around the circle would be the major arc here. And a semicircle is a part of a circle that measures exactly 180. So a semicircle measures exactly 180. Semicircle is exactly half a circle. And a semicircle has to be named with 3 letters. So if we're naming arcs, a minor arc is going to be 2 letters. A major or a semi will always be 3. So let's take this minor arc, for example, KL. To name that arc, I would put KL and then draw an arc symbol above it so that I know that that's an arc. If I wanted to name the same arc as a major arc, right, with the same endpoints, let me pick a different color here. I would go from K to L, but now I'm going around the other direction. So I need to use 3 letters here. So K, and then pick any letter between. Maybe I'll pick J, and then the other endpoint is at L. And so that would be that major arc. For a semicircle, we're going to look at exactly half the circle. So I'm going to look at this half of the circle, and I'm going to pick 3 letters. So I can pick either J or K, it doesn't matter, K, and then L because that's my other ending point. So that is the semicircle. 2 arcs of a circle are congruent if they have the same measure. We call those congruent arcs. And adjacent arcs are any arcs that share exactly one endpoint. So adjacent we know means next to, right? Adjacent should make us think next to. And so these 2 arcs that are next to each other that share one endpoint, those are adjacent arcs. So the next thing we're going to talk about is the arc addition postulate. And just like segment addition or angle addition, This says that we can add arc lengths together just like the lengths of adjacent segments. So if I want the measure of, and my arc symbols got erased here, arc RT, I could add together arc RS plus arc XT because those are adjacent segments that share an endpoint. So let's look at a couple examples. And again, my arc symbols got lost here. So I want the measure of arc IK. That is this whole arc. So to find that, I'm going to zoom in here. This central angle is 60. So I know this arc will have to be 60. This central angle is 90. So I know that this arc will have to be at 90. So arc IJK will be the sum of those two arcs, which would be 150 degrees. So now I'm going to erase that and let's look at another example. Arc JIL. So that's a major arc. I know that because it uses 3 letters. So again, we know that this arc here is 60. And arc IL here is a semicircle that has to be 180 degrees. And so JIL is going to be the sum of those arcs. So that's going to be 240 degrees. So let's look at this one. This one's a little bit more difficult. I'm just going to start by looking at the circle and trying to figure out everything I can. So I know that this central angle is 55, so I know that this arc is 55. I know that this central angle is 47, so I know the arc is the same. And the next thing that I see is that I actually have a pair of vertical angles here. So because I have those lines that create vertical angles, if this angle here is 47, this angle here also has to be 47. So that arc would need to be 47 degrees as well. And all of these are in degrees. So looking at these remaining 2 arcs that we have here, I'm going to use the fact that this line RU is a diameter, or the segment, and that's going to allow me to get those other 2 missing parts. Because this angle QPR and this angle over here have to create a semicircle. And so if QPR is 147, this angle here will have to be 133 to add up to 180. So the same idea for angle RPS. These 2 angles add up to 102 degrees. So to add up to 180, this would have to be 78 degrees. So now that I know all my angles, it's easy for me to find these arcs. So QS would be the sum of these 2 arcs. So 47 plus 78, which gives me 125 degrees here. And then RQT, we would go all the way around to there. So that would be the 180 from this semicircle here, plus the 47 over here. So that would be 227 degrees.